This video will introduce the Laplace Transform. This will enable us to solve differential equations, the kinds that we have done so far, plus some of the kinds we haven't been able to do so far. Let me introduce it. So let f of t be a function the Laplace transform of f of t is, here they use some sort of a script L, curly brackets, f of t, and that's the integral from 0 to infinity e to the negative s of t f of t dt. So whatever's in here inside of the curly brackets will go into this spot. We are going to spend this video evaluating the Laplace transform of various functions. So we'll start with the Laplace transform of just one. Of course, you can integrate this directly. S here, I'll explain this in just a minute, but S is really not related to the t that's integrating, so S is a constant. So if you were to make, say, a u substitution, u equals negative st, then du would be negative s dt. In other words, this becomes negative 1 over s e to the negative st from 0 to infinity. Now, if we make the assumption that s is a positive number, then negative s is negative. Well, e to a negative power with t involved, with that going to infinity, will automatically equal 0. But then, on the other hand, I have to subtract off when I plug in the lower limit, and that will be plus 1 over s e to the negative s times 0, or simply 1 over s. What they're doing is inventing another variable for these functions, and the usefulness of this won't be seen until I start solving some equations, but for right now we'll just do several examples to show how we actually calculate various things. And the whole thing is going to rely on the convergence of pretty much this thing. E to the negative power pretty much zeroes out when t goes to infinity, just about anything that you attach to it. Let's do the second example. This time I'll just do the function t. So I'll have e to the negative st times t dt. Now for something like this, I'll have to use integration by parts where u will be equal to t. So I'll set u equal to t, then du will simply be dt. dv is e to the negative st dt, and as before, v will be negative 1 over s e to the negative st. So this integral, you'll have uv, so I have negative 1 over s t e to the negative st from 0 to infinity, plus, since you subtract this diagonal here, the minus that was here makes it a plus. Remember, s is not involved in the integration, so I can bring it out front of the integral, just like it's a constant. And what do I have left in here? I have e to the negative st. And as before, you're going to have this piece, as t goes to infinity, this whole thing is going to go to 0. That assumes, of course, s is, I'm going to usually refer to s as a positive number of some sort. But the whole Laplace transform is a function of s. You'll see especially when I get done with this. So this will go to 0. Just so you know, let me put a little note here. And I'll continue on for a minute after I get this. If I have something like t to the n power, and I'm multiplying it by e to the negative t, then that thing, the whole thing goes to 0 as t goes to infinity. The point of it is that the exponential function, e to a negative power, overwhelms this function. And the way you see it is this. When you let t go to infinity, you notice that you have an infinity on top and an infinity on the bottom, so you use L'Hopital's rule. L'Hopital's rule says that you are permitted to differentiate the numerator and denominator. Well, you can see now if n minus 1 is still greater than 0, then the numerator is still going to infinity, and so is the denominator. Notice this denominator has not changed. So I can use L'Hopital's rule again. Well, you can see the same kind of things happening, infinity over infinity. I'm just going to apply L'Hopital's rule, n minus 2 more times. And eventually, you're going to end up with the limit as t goes to infinity. And once you've differentiated this n minus 2 more times, the numerator will be n factorial, and the denominator will just remain e to the t times t to the 0 if you should so want. But no matter what, this is just a number on the top, and the bottom is going to infinity. So this is equal to 0. So that brings me back to our problem that we had here. This part then, this is like t to the first power. S is some sort of a positive constant. So it's just like this situation here, except the n is only 1. That means that as I try to go to infinity, it will go to 0. So let me go ahead and bring this down. All right, so the limit as t goes to infinity is 0, so I'll get 0. And then you plug in 0, though. So I take minus this, which will be plus 1 over s. But there's a t there, so there'll be times 0 times e to the 0. Of course, that'll be 0. Here, we'll get negative 1 over s squared, e to the negative st, from 0 to infinity. Well, this here, once again, as t goes to infinity, it will 0 out, but I'll have to plug in the 0, and so I'll get 0 plus 1 over s squared. And so the Laplace transform of the function t is 1 over s squared. So you can see it is quite literally a function of s. S is a new variable that's introduced, and as I said, you'll have to wait and see why this is so great when I do other examples later on. But for now, let's content ourselves with actually computing these. Laplace transform of e to the t. That's 0 to infinity, e to the negative st times e to the t dt. Of course, these have the same base, so I can add the exponent, 0 to infinity, e to the negative s plus 1 t dt. And let me go ahead and integrate. I get got to be careful. I don't know much about s just yet. I get 1 over negative s plus 1 e to the negative s plus 1 of t dt, sorry, now this will work for what we want so long as s is greater than 1, because if s is greater than 1, this will be a negative number. So let me go ahead and say that s is greater than 1 for this procedure. That way, then we have a negative exponent here. As t goes to infinity, that will go to 0. And once again, we'll have 0 minus 1 over negative s plus 1 e to the negative s plus 1 times 0, which is negative 1 over negative s plus 1, or 1 over 1 minus s. In fact, if I try to do this for e to the negative t, I would get the integral from 0 to infinity, e to the negative st, e to the negative t, dt. That will equal 0, the integral from 0 to infinity, e to the, combine the exponents again, so I'll get negative s plus 1 t dt, and that will equal negative 1 over s plus 1 e to the negative s plus 1 t from 0 to infinity. And once again, we're going to try to figure out what s needs to be for this to work. I need this to be a negative number, s plus 1 to be negative. So we need s plus 1 to be less than 0. So s in this case would have to be less than negative 1 for this to work. But if that's the case, then when you try to do the limit as t goes to infinity, you'll get a 0. Plus, and as before, when you plug in 0, the exponent will be 0, and e to the 0 is 1. So you get 1 over s plus 1. In fact, if we want a formula, it might be a good idea to do e to the at, where a is a constant. And so that'll be the integral from 0 to infinity, e to the negative s of t, e to the at dt. I'll simply combine those exponents as before. 0 to infinity, e to the negative s plus a t dt. And when I integrate it, I get 1 over negative s plus a e to the negative s plus a of t from 0 to infinity. Now once again, in order for this to converge, I need this exponent to be negative, or at least this part. The t is going to be positive anyway since it's going to infinity. So I need negative s plus a to be less than 0. So negative s is to be less than negative a. S has to be greater than a in order for this to converge. If that's true, I will get 0 plus 1 over negative s plus a. I boo-booed. Minus that. And as before, I can change this to 1 over s minus a. Suppose I now do Laplace transform of t to the n is a natural number. That'll be the integral from 0 to infinity, e to the negative st, t to the n dt. Now what you'll do is apply multiple integration by parts. So where u would be t to the n, du would be n t to the n minus 1 dt. On the other hand, v would be e to the negative st dt, and dv, that is. V then will equal negative 1 over s, e to the negative st. So this integral will equal, so I'll have t to the n times that stuff. So negative 1 over s, t to the n, e to the negative st from 0 to infinity, plus, And what I'll do is I'll factor out, I'm putting a plus because when I subtract this diagonal here, it'll become positive. The n is a constant, and so is the s. So I'll be able to pull out the n over s in front of the integral. And what do I have left? I have e to the negative st, t to the n minus 1 dt. Now, I did go through the effort of showing by L'Hopital's rule that as t goes to infinity, all of this stuff will zero out. And then on the other hand, you'll plug in 0, so I'll get 1 over s times 0 to the n times e to the 0. Of course, that's just 0, plus n over s, the integral from 0 to infinity, e to the negative st, t to the n minus 1 dt. Same deal as before. I'll let u equal t to the n minus 1, du equal n minus 1, t to the n minus 2 dt, dv will equal e to the negative st dt, and so v equals negative 1 over s, e to the negative st. So my Laplace transform of t to the n, which is just this part right here, will be n over s times, so I've got my uv, negative 1 over s, t to the n minus 1, e to the negative st from 0 to infinity, plus, and this time I'll be able to, once again, I'm putting a plus again because that'll squash this negative. I'll have an n minus 1 over s, the integral from 0 to infinity, e to the negative st, t to the n minus 2 dt. Let me do a little bit of simplifying here before I go further. I'll keep my n over s out here. This, as it goes to infinity, you'll get 0, and then when you try to plug in 0, as long as n minus 1 is still positive, this piece will also be 0. So I'll just have 0 plus n minus 1 over s, 0 to infinity, e to the negative st, t to the n minus 2 dt. And let me go ahead and put it together here. And so when I multiply it through, I'll have n times n minus 1 over s squared, the integral from 0 to infinity, e to the negative st, t to the n minus 2 dt. Hopefully you can see a pattern emerging here. As I keep going, I'm going to keep going until I get to t to the 0. When will that happen? Well, on my next round, I'll get n minus 2 out here, then n minus 3 out here, and I'll keep growing with my s cubes too. This 2 matches the 2 that's there. So by the time I get to t to the 0, t to the 0 is like n minus n. What I will have is n factorial all over s to the n plus 1. I'm sorry, s to the n. The integral from 0 to infinity, e to the negative st, and this is by the time I will have dealt with all of the t's, and they're completely gone now. So now you can integrate directly, and you'll get negative 1 over s, e to the negative st from 0 to infinity. And as like all the other ones, as t goes to infinity, this will go to 0, but then when I subtract this negative, it will become positive 1 over s, because when you plug 0 into there, you'll have e to the 0. I'll get n factorial all over s to the n plus 1. In case you didn't know, what I'm doing is starting a catalog of different Laplace transforms of different functions, pretty much common functions that we use. Let's try one of our trig functions, cosine of kt, and that'll be the integral from 0 to infinity, e to the negative st, cosine of kt dt. Here k is just a constant. And I'm going to use integration by parts on this. You may have seen integrals like this before, where you break them up and then you gather things and then you take stuff to the other side. You'll see the details as I do this. I'm going to let u equal cosine kt. Then du will be negative k sine of kt dt. As the other one, as always, dv equals e to the negative st, and then v equals negative 1 over s, e to the negative st. So my Laplace transform of cosine of kt, so far what do we have? uv, I'll have negative 1 over s cosine of kt e to the negative st from 0 to infinity. And here, the two negatives do cancel, but I am subtracting this piece. So the triple negative will end up being a net negative here. I'll have k over s, the integral from 0 to infinity, e to the negative st, sine of kt dt. Now, cosine, the biggest cosine can ever be is 1. So if this is able to squash t to the n, cosine is nothing. So, and if you want to, you can do some L'Hopital's rule to see that that's going to happen. But so I'll get 0, but then I'll put in the minus. When I subtract off, plugging in 0 will become a plus. 1 over s, I'll have cosine of 0, e to the 0, minus, I'm going to leave that for a minute, k over s, the integral from 0 to infinity, e to the negative st, sine of kt dt. Of course, this here is 1 over s. And as before, I'm going to use partial fraction, or integration by parts again. My u will equal sine of kt. My du will equal k times cosine of kt dt. dv equals e to the negative st dt. v equals negative 1 over s, e to the negative st. So we have the Laplace transform of cosine of kt. That will equal the 1 over s I'm just bringing down. And then here I'll have my negative 1 over s sine of kt e to the negative st from 0 to infinity. And then when I subtract, I'll get a plus k over s, the integral from 0 to infinity, e to the negative st cosine of kt dt. And then I'm going to have, well, let me go ahead and evaluate this before I actually start multiplying things through. For this piece here, as t goes to infinity, you get 0 as normal. E to the negative st overwhelms sine. But then, when you try to plug in 0, well, sine of 0 is 0. So we get a big fat 0 there for all of that. Let me go ahead and multiply through by the negative k over s. So that minus k squared over s squared, integral from 0 to infinity, e to the negative st, cosine of kt dt. And this, of course, is equal to the Laplace transform of cosine of kt. Well, I don't know if you recognize it by now, but this is the Laplace transform of cosine of t here. So this equals 1 over s minus k squared over s squared times the Laplace of cosine of kt. Now we're really only interested in values of s and t and all that kind of stuff for which all of these integrals converge to a finite number. What I'm going to do is add this chunk to both sides, and that will give me the Laplace of cosine of kt plus k squared over s squared, the Laplace cosine of kt. That equals 1 over s. I can factor the Laplace out of both parts of this, and I'll end up with 1 plus k squared over s squared Laplace cosine kt equals 1 over s. Let me simplify this over here. If you do that, you'll get s squared plus k squared over s squared. I guess I don't need the parentheses, but it doesn't hurt. And then I'll go ahead and multiply by the reciprocal of this. An s will cancel. And here's our formula for the Laplace transform of cosine of kt. S over s squared plus k squared. For the student, show that the Laplace transform of sine of kt equals k over s squared plus k squared. So while it's similar, it's not exactly the same. You'll use exactly the same methods to integration by parts to get something to the other side and solve for the Laplace transform of sine. It's exactly the same thing as what I did. One of the things that makes the Laplace transform so desirable to use is something they call linearity. What that means is the following. If I take the Laplace transform of, let's say I have a function, I don't know, yeah, why not? I'll use C1 f of t plus C2 g of t. Well, let me throw it into the integral. And where you plug in the function, I will put all of this stuff into that spot. And the rest of the stuff just follows from what the integral is capable of doing itself. I can break the integral up into a sum of integrals. And then with any integral, you can bring the constant out front. And of course, this is the Laplace transform of f. And this helps us with lots of computations. So all I really have to do is get a collection of basic functions that I can do the Laplace transform for, and then this will perform some magic to give me more complicated functions. For example, I think I'm on example 8. Suppose I want to do the Laplace transform of cosine of 5t plus sine of 2t. Well, I can break this into the Laplace of cosine of 5t plus the Laplace of sine of 2t. And then above, I just developed the formulas for those things. Here the k is 5, so we have s over s squared plus 5 squared, plus, and here the k is 2. And for sine, the k was in the numerator. We had k over s squared plus k squared. So I can break it up very nicely like that. Suppose I want to do the Laplace of 2t minus 1 to the third power. Now, that doesn't have a multiplicative thing. Like, I can't bring this third power out. There's nothing like that. I have to multiply this all out. FOIL it out, whatever you want to do. I'm going to use something called the Binomial Theorem to do this. And you may have seen it. I'm going to write the steps for it just for you to check. But they look like this. This is where you do something called the binomial coefficient. And then I take the 2t gets raised to the third power, but the negative 1 gets raised to the 0. Plus, and then I have 3 choose 1, 2t squared, negative 1 to the 1, plus 3 choose 2, 2t to the 1, negative 1 squared, and then finally plus 3 choose 3, 2t to the 0, negative 1 to the third. If you would like, go ahead and look up the binomial theorem to see how this actually works if you don't know this or don't remember it. But here's what we get. This 3 choose 0 turns out to be 1. So all I have to worry about is 2t to the third, because negative 1 to the 0 is also 1. I'll have 8t cubed. Then for the next piece, 3 choose 1 is 3. Then I'll have 4t squared, but it'll be negative. So I'll have negative 12t squared. Here, the negative 1 squared will be positive, so I can put a plus. 3 choose 2 is 3. 3 times 2t is 6t. And then on the last one, 3 choose 3 is 1. 2t to the 0 is 1. And we just have minus 1. But this is really nice because now I can break this up. 8L of t cubed minus 12L of t squared plus 6L of t minus L of 1. And let's go ahead and put all of those in. Now, when I had the formula for t to the n was n factorial over s to the n plus 1. So I'll have 8 times 3 factorial all over s to the 3 plus 1 minus 12 times 2 factorial all over s to the 2 plus 1 plus 6 times, well, here the n is 1, so it would be technically 1 factorial all over s to the 1 plus 1, and then lastly minus 1 over s. And should you choose to, you can do a little simplifying here. I get 3 factorial 6, so I get 48 over s to the 4th minus 24 over s cubed plus 6 over s squared minus 1 over s. So it's very nice the way it breaks things up like this. That way we've already covered these basic functions like that. How about the Laplace transform of e to the negative 2t minus 5? Well, this I can rewrite as the Laplace of e to the negative 2t times e to the negative 5. Well, e to the negative 5 is simply a constant. So I can bring it out front of the Laplace. And then we have the formula for that. Do you remember that e to the at was 1 over s plus a, so we have e to the negative 5 divided by s minus 2. My mistake, that was a plus. It was 1 over s minus a. And one last example. Most of the homework for the introductory stuff is doing exactly what I'm doing, trying to evaluate the Laplace transform of different things that you're inputted. So check this out though. Suppose our function is this. Suppose it's 0 when t is less than or equal to, or t is greater than or equal to 0 but less than pi over 2. And suppose that it's cosine of t for t greater than or equal to pi over 2. So the Laplace transform I'll plug it in, 0 to infinity, e to the negative st, f of t, dt. Well, from 0 to pi over 2, this f of t is 0. So what I have here is the integral you can break up in the following manner. So I can break it up from 0 to pi over 2 and then from pi over 2 to infinity. Well, for this piece, this is 0. On this piece here, when it's from pi over 2 to infinity, the function itself is cosine of t. Now from here, you can go ahead and use parts, integration by parts on it. So let me write this for a second because I'll need it later on. And as before, we'll do u equals cosine of t, du will equal negative sine of t, dt, dv will equal e to the negative st, dt, and v equals negative 1 over s, e to the negative st. So my Laplace transform of f of t will equal, so this part right here, I'll have negative 1 over s cosine of t, e to the negative st from 0 to infinity. Then when I subtract this diagonal here, these two negatives cancel with the addition of the other negative. I'll have a negative. I'll pull the 1 over s out front. Integral from pi over 2 to infinity, e to the negative st times sine of t dt. Of course, as t goes to infinity, I get 0, but I can plug in the 0 to get 1 over s. And partial fractions come, or partial, I don't know why I keep saying that. Integration by parts comes to rescue again. This time u equals sine of t. Du equals cosine of t dt. dv equals e to the negative st dt. And then v is negative 1 over s, e to the negative st. And so my integral will be 1 over s. Then I'll have minus 1 over s times negative 1 over s, e to the negative st sine of t from pi over 2 to infinity. And then I'll have plus 1 over s, the integral from pi over 2 to infinity, e to the negative st cosine of t dt. Let's go ahead and do some simplifying here. I'll get 1 over s minus 1 over s, bracket. As t goes to infinity, you do get 0. And then I can plug in pi over 2 because sine of pi over 2 is 1. And I'll also get a pi over 2 up here. So I'll get 1 over s e to the s pi over 2 plus 1 over s, the integral from pi over 2 to infinity, e to the negative st cosine of t dt. Let's do some simplifying here. I have 1 over s minus 1 over s squared, that times that, e to the s pi over 2 minus 1 over s squared, integral from pi over 2 to infinity, e to the negative st cosine of t dt. Of course, this is all equal to the Laplace transform of f of t. Now you notice that when I plugged in f of t, the 0 to pi over 2 part disappeared and vanished. This stuff right here is the Laplace transform of f of t. So let me go ahead and put 1 over s minus 1 over s squared e to the s pi over 2 minus 1 over s squared times the Laplace transform of f of t. So I will add that to the other side. And that's going to equal 1 over s minus 1 over s squared e to the s pi over 2. I'll do as I've done before. I will factor out the 1 plus 1 over s squared L of f of t. That equals 1 over s minus 1 over s squared e to the s pi over 2. Did I make a boo-boo? Before I go further, I did make a mistake. My problem was right here. That would have been a pi over 2. And so I was wrong that this was a 1 over s here. We'll go ahead and cancel it, because cosine of pi over 2 is 0. Let me go ahead and get rid of that. And I will fix my mistakes now, and we'll carry on. I'll just start erasing it for now. So anyways, I still have the same thing going on here. I'll make this one a simple fraction. I'll have s squared plus 1 over s squared, the Laplace of f of t. That equals negative 1 over s squared e to the s pi over 2. I'll go ahead and multiply by the reciprocal of that fraction. So the Laplace transform of f of t, that will equal negative 1 over s squared e to the s pi over 2 times s squared all over s squared plus 1. I can cancel the s squareds, and it looks like I have negative e to the s pi over 2 divided by s squared plus 1. And another mistake. Before I'm able to finish this video, when I plugged it into t here, I did not account for this negative, 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 and I have to put a negative in all of these spots to fix my mistake. Now, the answer finally matches with my notes, so I think it's correct. Well, that's all I have for there. The next thing we'll do is start to work on setting the ground for solving differential equations with this method.